Have you ever looked up at the night sky and wondered about the very beginning, not just the first stars, but the first second after the Big Bang? In that chaotic, ultra-dense cosmic soup, tiny pockets of space-time collapsed, forming objects so ancient they predate the oldest stars, primordial black holes. Born from the fabric of creation itself, these cosmic ghosts could hold the keys to our universe's deepest mysteries: dark matter, cosmic inflation, even the seeds of galaxies. They challenge everything we know about gravity, cosmology, and our own origins. So get ready as we explore the top 10 most mind-bending theories about these primordial phantoms. Let's dive in. Dark matter, a cosmic enigma that has captivated and challenged scientists for decades. It's everywhere, permeating the cosmos, shaping the majestic spiral arms of galaxies, bending light from distant quasars in a cosmic dance of gravity. Yet despite its profound influence, it remains invisible and stubbornly undetected by our most sensitive instruments. For decades we've tirelessly searched for exotic particles, weakly interacting massive particles or WIMPs and axions, hoping to unveil the nature of this elusive substance. But what if the answer has been staring us in the face all along? What if the solution lies not in the unknown but in something we already know: primordial black holes? Imagine the universe in its infancy, filled with a vast population of ancient black holes, remnants from the Big Bang itself. Ranging in size from asteroid-sized, all the way up to several times the sun's mass, a hidden population lurking in the shadows. These primordial black holes would be virtually invisible, betraying their presence only through their immense gravitational pull. They'd be perfect dark matter candidates, silent, unseen, and exerting a gravitational influence that shapes the very structure of the cosmos. Formed in the chaotic aftermath before atoms even existed, forged from pure gravity in the extreme conditions of the early universe. They would be scattered throughout the vast galactic halos surrounding galaxies like our own Milky Way. If they exist in sufficient numbers, we could potentially spot them through a phenomenon called gravitational microlensing, briefly brightening distant stars as these black holes pass in front, acting as a cosmic magnifying glass. Telescopes around the world and in space are meticulously searching for these fleeting flickers right now, sifting through the starlight. Finding the right pattern, deciphering the subtle signals, could revolutionize our understanding and reveal that dark matter is not made of exotic particles, but of black holes. Not elusive particles that barely interact with matter. Instead of chasing after ghostly particles in underground laboratories, picture countless tiny black holes drifting silently and invisibly between the stars, a hidden population shaping the cosmos. The universe might be haunted, not by ghosts in the traditional sense, but by the literal gravitational ghosts of its own violent creation. The hunt is on, and the stakes couldn't be higher as we try to unravel one of the biggest mysteries in science. Will the existence of primordial black holes solve the dark matter mystery, or will the true nature of dark matter remain elusive? To truly grasp the nature and significance of primordial black holes, we need to embark on a journey back in time. We must rewind to the universe's very first fraction of a second, a period of unimaginable energy and density. This was a time long before the formation of stars, galaxies, or even the most basic atoms. The universe, in its infancy, existed as a seething, hot, and incredibly dense plasma, a primordial soup of elementary particles. Within this plasma, quantum fluctuations manifested as tiny ripples in the very fabric of space-time. The vast majority of these ripples, these minute disturbances, smoothed themselves out as the universe expanded and cooled. However, in certain rare regions, the density of matter became so exceptionally high that the relentless force of gravity overcame the outward push of the universe's expansion. These regions underwent rapid and catastrophic gravitational collapse, instantly forming black holes of varying sizes. Unlike the black holes we observe today, these weren't born from the death throes of dying stars. Instead, they arose from the spontaneous and immediate implosions of space-time itself in the early universe. And these are what we call primordial black holes. They are essentially fossils, frozen in time, offering a unique glimpse into the universe's very birth. The size of a primordial black hole is intrinsically linked to the precise moment it came into existence. The earlier they formed, the smaller they are. The later they formed, the larger they become. Imagine a primordial black hole that originated at the Planck time, the earliest moment we can theoretically probe. Such a black hole could possess a mass as light as a single grain of sand. Conversely, A primordial black hole that took shape just 1 second after the Big Bang could potentially reach hundreds of thousands of times the mass of our own sun. These aren't merely astrophysical objects, they're fundamentally cosmological entities. They serve as direct probes, offering invaluable insights into the physics that governed the Big Bang. Therefore, discovering even a single primordial black hole would be akin to unearthing a perfectly preserved fossil, a pristine artifact from the very dawn of time. Each and every PBH represents a relic, a tangible and direct connection to the universe's earliest moments, a link across cosmic time. They are, in essence, the ultimate cosmic time capsules, preserving information from an era we can only theorize about. What profound secrets, what groundbreaking revelations could these primordial black holes ultimately reveal about the origins of our universe? When you think black hole, what comes to mind? You probably picture a dead star, a stellar remnant collapsing under its own gravity, leaving behind an incredibly dense object. Or perhaps you envision a supermassive giant lurking at a galaxy's center, exerting its gravitational dominance over everything around it. But primordial black holes are different. They represent a completely distinct class of these enigmatic objects. They weren't born from dying stars, but rather from the extreme conditions of the early universe, moments after the Big Bang. Their masses could be anything. The possibilities are truly mind-boggling. From something as small as a mountain to something as large as the moon, or even intermediate sizes, filling the gap between stellar and supermassive black holes that we haven't fully explored yet. Unlike stellar black holes, which are typically formed with a significant amount of angular momentum and therefore spin rapidly, primordial ones might have little or no spin, making them fundamentally different in their behavior and interactions. Their distribution across the cosmos is also expected to be unique. While stellar black holes are primarily found clustered within galaxies where their progenitor stars lived and died, primordial ones could be scattered virtually everywhere, a testament to their formation in the very early homogeneous universe. They might even reside in the seemingly empty intergalactic voids, far from any galaxy. Finding a small, non-spinning black hole in deep space all alone would be a smoking gun, strong evidence pointing towards a primordial origin. They're cosmic nomads wandering the universe untethered to stars or galaxies, relics of a bygone era. Their existence would fundamentally rewrite our understanding of black holes and the universe's early history. They could fill crucial gaps in the black hole mass spectrum, providing insights into the formation of these mysterious objects. Primordial black holes are the universe's true wildcards, holding secrets to the cosmos's deepest mysteries. If we find just one, confirm its existence, it changes everything we thought we knew about the universe. Are we ready for that paradigm shift, for that groundbreaking discovery? The search continues, and the universe awaits. Cosmic inflation, the universe's explosive growth spurt, solves big cosmological puzzles but lacks direct proof. Some inflation models predict amplified density ripples perfect for forming primordial black holes. If we find a specific population of PBHs with the right mass distribution, it's like finding dinosaur footprints, undeniable evidence of inflation. Detecting these PBHs would confirm inflation and help us choose between competing models. The search for primordial black holes becomes a test of our universe's earliest moments. The universe itself is our laboratory. Will PBHs be inflation's smoking gun? Gravitational waves let us hear the universe ripples from black hole mergers. If primordial black holes exist, some should collide, sending out unique gravitational wave signals. LIGO and Virgo can detect these cosmic chirps. A merger between two tiny black holes, smaller than any formed by stars, would be a clear sign of something primordial. The frequency and rate of these events could reveal the hidden population of PBHs. So far, most signals match stellar black holes, but the search is young. Every new detection is a chance to catch a whisper from the dawn of time. Will we hear the echoes of creation? How did the universe get so lumpy so fast? Standard models say tiny fluctuations grew slowly, but primordial black holes could have jump-started galaxy formation. Each PBH would act as a gravitational seed, gathering dark matter and normal matter more efficiently than random fluctuations. Galaxies could form around these seeds, explaining why we see massive galaxies so early in cosmic history. Observations from the James Webb Space Telescope show surprisingly mature galaxies in the early universe. PBHs as seeds make this rapid assembly possible. They're not just relics, they're cosmic architects. Did primordial black holes build the universe we see today? The cosmic microwave background is our universe's baby picture, an afterglow from 380,000 years after the Big Bang. If primordial black holes existed, they'd leave fingerprints on the CMB by heating surrounding matter or distorting temperature fluctuations. Precision measurements from satellites like Planck show the CMB is nearly perfect, limiting how many PBHs can exist. For certain mass ranges, PBHs can only be a tiny fraction of dark matter. The CMB acts as a cosmic detective, ruling out many PBH scenarios, but some windows remain open. The search for their subtle marks continues. Stephen Hawking showed that black holes aren't truly black, they slowly evaporate via Hawking radiation. For massive black holes, this process is glacial, but for tiny primordial ones, it's rapid and dramatic. A PBH with the mass of a small asteroid would be evaporating right now, ending in a burst of high-energy gamma rays. Gamma-ray telescopes scan the skies for these final flashes, unique signatures of evaporating PBHs. So far, no unambiguous signals have been found, placing limits on how many small PBHs exist. But a single detection would confirm both primordial black holes and Hawking radiation. It would be a monumental discovery. The universe could be lighting up with the last breaths of its oldest ghosts. Are we watching closely enough? The search is far from over. After the CMB, the universe entered the cosmic dark ages. No stars, just cold gas. The first stars and galaxies eventually ionized the universe, but we may need more ionizing photons than they could provide. Accreting primordial black holes could have acted as tiny quasars, emitting X-rays and UV light to help ionize hydrogen. They might have sparked the end of the dark ages, making it easier for the first stars to finish the job. The James Webb Space Telescope could reveal if PBHs played this role. If so, the pattern of reionization would look different, more uniform and patchy. Did primordial black holes light the universe's first dawn? Now let's venture into the speculative. What if primordial black holes are more than cosmic relics? Some theories suggest they could be evidence of multiverse collisions or even gateways to extra dimensions. In string theory, a black hole might connect to other dimensions, subtly altering its properties. Another idea, the singularity inside a black hole could spawn a new universe, a baby cosmos budding off from ours. Every PBH could be a parent universe. Maybe our own universe was born from one. These ideas are wild, untestable for now, but they push us to rethink reality. Primordial black holes force us to confront the deepest questions about space, time, and existence. They're not just objects, they're theoretical laboratories for the impossible. What if the truth is stranger than we can imagine? 10 mind-expanding theories. Primordial black holes as dark matter, cosmic seeds, even portals to other universes. Finding them would reshape our understanding of everything, connecting the quantum realm to cosmic structures. The search is a testament to human curiosity, using every tool from gravitational waves to gamma rays. Each theory offers a new vision of the cosmos, but only evidence will reveal the truth. The universe is stranger than we can imagine, and our quest is just beginning. Keep looking up. If you enjoyed this video, don't forget to subscribe, like, and comment below. Your support helps us bring more amazing content to you. Hit that notification bell so you never miss a moment of cosmic wonder. Together, let's keep exploring the mysteries of the universe, one mind-blowing discovery at a time.